Hello everyone, this is Dr. Webb, and in this video we will be reviewing how to set up integrals to calculate volumes of revolution. So let's start with the disk and washer method. And so first we need our volume of revolution. And so let's draw that out. So we're going to have two functions, one above the other. So the first one we'll call f of x. The other one we'll call g of x. We need some x values, so we'll be looking at the region bounded between x equals a and x equals b. And then we're going to think about the volume that we get when we rotate this around the, say, x-axis. So we're rotating around the x-axis right now. And so these are going to get spun around, creating, in this case, kind of a weird vase shape. And back here, same thing back there. So this will go something like that on the inside. So we want to be able to calculate the value of this. So let's think about what one of these slices is going to look like, and this is where the name disks and washers comes from. So let's clean up this picture a little bit. Okay, so now we have just the region again, and let's imagine if we're looking at some x value in between, taking this little slice around x. And what happens to this slice? Well, as this slice gets spun around, it's going to create this kind of washer shape. And so this is where the name comes from. And so if we were to take this washer right here, let's bring it out and let's turn it 90 degrees so that we can see it facing out. And so the outside is going to be a big circle right there. You have a smaller circle on the inside. We have the axis of rotation coming straight out from us in this picture. Right? And so let's add some colors in here just so it's clear what we're talking about. So this outer circle is this outer circle on our cross section. The inner circle turns into this inner circle. And so this dot in the middle, this axis of rotation, it is talking about the x-axis. And so that's coming straight out from us. And so the big question is, what's the area enclosed in the washer? And that's not so hard, because really it's a big circle with a little circle cut out, and we know how to take areas of circles. And so this big circle is going from the x-axis to the top of the function f of x. And so that's, think about that big radius right there. And so if it's going from the x-axis up to y equals f of x, the length of that is exactly f of x. For the smaller circle, it's going from the x-axis just to g of x. And so this smaller radius is g of x. So the area of the washer, let's call it A, well, it's going to be the big circle minus the small circle. And so the big circle here, it's a circle with radius f of x. So the area, if it has radius f of x, is going to be pi times the radius squared. So that's pi times f of x, quantity squared. And then the small circle, its area is going to be pi times the radius of the small circle squared. And that small circle has radius g of x. And so there's our area of our washer. So now how do we get this volume out of it? Let's give ourselves some space. Okay, we've shrunk that down and give ourselves some more space. And so if we want to calculate now the total volume of the big volume of revolution, well, the volume is going to come from taking this area that we calculated for each x value and integrating it from a to b dx. Right? And so you can think about this volume is coming from, well, you're adding up all these little areas. Or another way to think about it is the dx here is kind of sorta is thinking about a tiny bit of width in the x direction. And so if you take that tiny bit of width in the x direction, multiply it by the area of the base, that's giving you a tiny bit of volume. Okay, and so integrating area gives you volume. And we know what a of x is because we have it right above. And so I'm going to get our formula. And we can pull the pi's out of everything. But it's the big radius squared minus the smaller inner radius squared times pi all times dx. And that gives us our formula for how to calculate the volume using discs and washers. How does this change if rather than rotating around the x-axis, we want to rotate around the y-axis? And so now we have some region. Since we're rotating around the y-axis this time, we're going to need to think about our functions as being functions of y. And so let's give ourselves two functions of y. We'll call the outer one c of y. We'll call the inner one d of y. And then we need two y values. Let's call it r and s. And this will give us our region. And now we are spinning these around the y-axis. So this will be, if you were to do this and think about what this looks like, it would look kind of now like a upward facing vase, roughly. Let's get rid of that extra drawing. And so let's think about what our cross sections look like here. And so now, looking at our cross sections, we'll think about picking some y value between r and s. And so we get this slice here, and we're going to get our washer again. So we're going to have an outer radius coming out, and then we'll have an inner radius. This is not very much to scale, but that's okay. And so similar before, the area of this washer, if we were to pull it out, rotate it so it's facing us, it's just going to be a big circle with a little circle cut out. And so our area, and now we're thinking about this in terms of y, is going to be the radius of the big circle is going out from the y-axis all the way out to c of y. And so the area of the big circle is going to be pi times c of y squared. And then we need to subtract off the area of the inner circle. And the radius of the inner circle is going from the y-axis to d of y. So it's going to be pi of d of y squared. And so again, we've got big circle minus the little circle. And so let's give ourselves some more space. What's our volume going to calculation going to be here? Well, our volume is now we're going to be integrating in terms of y, and we're going to be going from r to s of, again, we're integrating this area function, a of y, and so that's going to be r s pi of, factor that out, c of y squared minus d of y squared dy. Okay. So the thing to remember with disks and washers is if you're integrating around the x-axis, then your integral is going to be in terms of x. Whereas if you do something around the y-axis or even parallel to the y-axis, then everything's going to be in terms of y. And so this is the basic rule for disks and washers. Okay, so now let's talk about thinking about this differently. Let's think about it in terms of cylindrical shells. And so the way the setup usually is for cylindrical shells is if we have our functions f and g in terms of x, and again we have a and b, but the big difference now is for this region, instead of rotating around the x-axis, we're going to be rotating around the y-axis. And so this will give us some kind of shape like this. Okay, coming big out that way, big out that way. So big upward facing thing with the hole down the middle here. Let's clear out these extra drawings. Get back to just our region. Okay, here we go. And so how do we get the shells out of this? Well, again, we're going to think about taking some x value between a and b, gives us a little strip between f and g, and we're thinking what happens just to this strip as it gets spun around. Right? So it's like a little vertical strip getting spun around. What shape is it going to create? Well, it's going to create sort of the outside vertical part of a cylinder. Sort of a cylinder where we don't have any top or bottom. So it's you kind of take a cylinder and cut off the top and the bottom. So this is where the idea of cylindrical shell is. It's the shell on the outside of a cylinder. And so same as with disks and washers, we have to kind of think about what is this area that's being cut out here. Right? So right now, this is not great to scale, but we get an idea of this. So this is a shell going out this way. And so the height here that's going around the whole way across, well, this is the distance between f of x and g of x. So this height here is going to be f of x minus g of x. And then the top part of this that's going to be a circle, and that's a radius right there. And so how far out are we from the y-axis? Well, the y-axis is at x equals 0, and we're going from x equals 0 all the way out to x. And so that length there is x. Okay. And so now what we're going to do is we're going to think about this outside of the cylinder, and it's wrapped up in a circle. Well, we're going to think about sort of taking one place, taking some scissors, and cutting along that, and unwrapping this cylinder, and so that we have it as one big rectangle, right? So if we make this as one big rectangle, the blue ends are going to be going up and down, and they're still going to be f of x minus g of x. And what's the top of this rectangle going to come from? Well, the top is coming from the circumference of this circle, right? It's the circumference gets cut out all the way, and it's a circle of radius x. So if it's a circle of radius x, what's the size of the circumference? Well, that's going to be 2 pi times x, right? And so the total area here is we just have a rectangle. It's 2 pi x for the top part times f of x minus g of x for the vertical part. And let's shrink this down again and give us some space. So now that we know what the area is, how do we get the volume? Well, it's the exact same process as before. So the volume is still going to be adding together all of these areas, and we're adding them together in the form of an integral. So we're still going to be integrating this area function in terms of x from a to b, but now this area function looks a little bit different. It's now going to be 2 pi x times f of x minus g of x, all times dx. And so again, this f of x times g of x, this is talking about the height of the shell. And the 2 pi x, this is coming from the circumference of the shell. And if you imagine cutting the shell open into a big rectangle, this is just a rectangle where one side is length of the height, the other side is the length of the circumference. Multiply them together, and that gives you the area. So the really big difference with shells from discs and washers is that for shells, if we're rotating around the y-axis like we were here, then our integral is going to be in terms of, well, what variable was it in terms of here? It was in terms of x and not y. So for cylindrical shells, the axis that you're rotating around, or if you have it horizontal to the y-axis, then your integral is going to be in terms of x. Whereas if you're rotating, help if spelling was somewhat close, around the x-axis, well then you need all of your functions in your integral in terms of y. So for cylindrical shells, the axis of rotation is different than the variable that you're integrating in terms of. You're changing variables between them. So now let's do an example of this. I don't think we're going to work this integral out all the way, but we're just going to set it up. So we're going to think about the volume that we get when we take the area enclosed by y equals e to the x, y equals e cubed, and the y-axis, and then we're going to revolve it around the y-axis. So first let's draw a decent enough picture of what we're talking about here. So e to the x, that's my exponential function, goes through the y-axis at 1. Y equals e cubed, that's just going to be a horizontal line going across, and e cubed is actually pretty big, and so this is not to scale, but good enough. And so this is going out this way, and then here's my y-axis, and so my region here is this area enclosed right here, and then we are going to, it says spin this around the y-axis. Okay, so we're taking this region and spinning it around the y-axis. Okay. So we're going to set this up both with discs and washers and with cylindrical shells. So let's do discs and washers first. So y equals e to the x. Now if we're doing this in terms of discs and washers, we're rotating around the y-axis here, and so that means that we're going to have to rewrite everything in terms of y. Right? So if we're looking at this region in terms of y, well, first thing I got to do is rethink about what y equals e to the x is in terms of y, and the inverse of e to the x is natural log, and so this is x is equal to the natural log of y. Okay, and so now we're doing this for discs and washers. So if I think I take some y value, think about the strip going out in the y direction of that region, and then it's getting spun around. And in this case, there is no inner circle. It's going all the way, the region goes all the way into the axis of rotation, so we just have a big outer circle. And so what's our big outer circle looking like? Well, the radius here is going from the y-axis to natural log of y, and so our big radius here is going to be natural log of y. Okay, and so our basic integral is going to be, we're going to be integrating the area function, in this case in terms of y dy, and our bounds are going from y equals 1 to y equals e cubed, and our area function, so it's going to be just one big circle, y-axis is the middle of it, and the radius of this is natural log of y, so our area is going to be pi times natural log of y squared dy. And so this was a pretty straightforward integral to set up. It's probably not, my choice of my favorite integral to try and solve, but we can set it up. And you could go through and use integration by parts or something like that to go and work this integral out. Okay, what about if we want to do this by shells instead? Let's clear some of this out. Maybe make it smaller up there. So we'll draw the same region. But if we're doing this in terms of shells, now we're going to be doing everything in terms of x. And so we need to rewrite everything in terms of x. And so this region right here in terms of x, well, it's starting on the y-axis, so that's x equals 0. And then it's stopping when y is equaling to e cubed, or when e to the x is equal to e cubed. And so what's the x value that that's happening at? Well, that's happening at x equals 3. Okay. And so we're still rotating in terms of y. And so now to build the shells, now we're thinking about taking some, what's the area we get when we take some x value and looking at that shape, looking at that little strip right there, And what happens when we spin that around the x-axis? Right? And so here, the height of this shell is going to be, well, it goes, the top of it is at e cubed, the bottom of it is e to the x, and so this height here is going to be e cubed minus e to the x, and then we have our big circumference up here, and so the circumference is coming from a circle whose radius is x again, and so to make our integral for this, now we're doing the area of our shell, and so that's an area in terms of x, dx, and our region is going from x equals 0 to x equals 3. But our area function now, if we think about taking this shell, cutting it open, and flattening it out, well, now the height is coming from the height of the strip, and so that's e cubed minus e to the x. And then the top of this is coming from the circumference, and the circumference is, it's a circle of radius x, and so the circumference here is 2 pi x. And so our area function here is going to be 2 pi x times e cubed minus e to the x dx. Right? And so now we have two different integrals representing the same volume. So the first one, again, this one was in terms of disk because it wasn't really a washer. And so since we rotated around y, this integral is in terms of y. And then secondly, we did bicylindrical shells. And so since we rotated around y, this integral is in terms of x. And so if you wanted to get the actual volumes here, now you could pick one of these two and work it out. And of these two, which one would you pick? Honestly, I would probably pick the second one. I think in both of these you're going to have to use integration by parts. And the second one, I think it's pretty much just one step of integration by parts. The first one, I think you'd have to do 2 steps. So the first one would probably be a little bit easier. And this also, knowing how to do both of these techniques, one of the benefits of it is if you have some region and you can set it up in 2 different ways, well, then that gives you 2 different integrals to choose from to actually solve. So if you can figure out how to set up both of them, then you can look at the 2 integrals you get and say which of these is easier to do, and then pick that one to complete it. So that is all I have for this video. I will see you again soon.